visiting from New York, Lehman College. And he's going to speak about the Hodge and the Rham Chern character of polymorphic bundles.
Thank you for having me. So this is joint work with Shane Miller, Micah Miller, and Thomas Stradler. I want to talk about characteristic classes. So what are characteristic classes? Most of you know, but let me just say very briefly what these things are like. So suppose you have a surface in a three-dimensional space, an embedded surface. There is something called the Gauss map, where you look at the tangent space at a point and look at the normal unit vector. And then for every point, you mark that normal unit vector as a vector inside the unit sphere, on the unit sphere. And then as you vary from point to point, this surface starts wrapping around this sphere. And basically, you count the number of times this wraps around that, in the sense that you look at maybe a point, and you look at the pre-image, and then you see there are like these tangent spaces. Some of them are mapped to this tangent space with the correct orientation, some with the wrong orientation. You take the difference, and that would be the number of times it has wrapped. Or if you want to use some analytic technique, you can take the volume form here and pull it back, and then integrate it over the surface. If it's oriented, you can do that. And then you get a number. Turns out that number is always an integer. And it's some invariant which is proportional to the genus. It's 1 minus the genus, for example. Okay, and that's the simplest example of what a characteristic class is, because this is fairly general in the sense that instead of taking these normal vectors, I could have just taken the tangent spaces and then map it not in the space of vectors, but the space of all tangent spaces, or space of all two-dimensional subspaces of the three-dimensional space. These are called Crossmanions. And once you take that point of view, you can easily see that this generalizes to any dimension. You can take any submanifold of Rn, which basically by Whitney's theorem, these are all manifolds, and take this map. It lands in some Crossmanion, and these Crossmanions tend out to have interesting forms reminiscent of the volume form here. So you can always pull those back and integrate and get some invariant. Those are called the characteristic classes. Now, how do you get your hands on these? So one way would be to actually construct this map, or put yourself in a situation where you are given such a map. These maps are called classifying maps. But differential geometers like to approach this using a familiar differential geometric data. For example, what happens if I have a connection or a metric or something of that sort? So it turns out that this is fairly general and can be done using what's called Chern-Bay theory. So what is Chern-Bay theory? Chern-Bay theory says start with any vector bundle and put a connection on it. So from here, the discussion was a real discussion. So I'm going to now switch to complex vector bundles because they're a little nicer to work with. So these are complex vector bundles. And suppose you have a connection on this, which allows you to identify nearby fibers. And now there's something you can do out of this connection. You can get a two-form, which is called the curvature. And this is the two-form with values in endomorphisms, let's say of the base, with values in the endomorphisms of this vector bundle E. And then you can exponentiate this. So you get a 0 form, a 2 form, a 4 form, etc. And these would be closed by what's called the Bianchi identity. And then you can take trace. So by Bianchi identity implies that when you take trace, these become real valued forms that are closed. And then they would therefore represent certain classes. And these would calculate these pullbacks. basically. The cohomology classes of these, calculate the cohomology classes of these pullbacks of the analogs of the volume form, so to speak. Okay, but now you may say, well, it would be nice, and this was the point of view that was espoused by Bott quite a bit. It was an advocate of writing invariants of vector bundles in terms of the transition function. So you can ask yourself, well, if a vector bundle is just a sequence of GIJs, such that GIJs are defined on, let's say, UI intersection UJ is going to some GLNR, GLNC in this case, satisfying GIJ, GJK equals GIK. If the vector bundle is just this data, can you write down a formula in terms of this data for these invariants? It's a very reasonable question, and over the years has been addressed in many different forms. And I'm going to present to you one form of answering this question, which I think is kind of a very complete answer in the sense that it not only applies to this situation, but it also helps you understand equivariant characteristic classes and characteristic classes of stacks and all that. So
quick question. So already here, R can be expressed in terms of these GIJs. Right?
You can, yeah.
You have these numbers.
Right. You can go through that and express them.
And then you can unravel that with trace of e to the r.
Right.
GIJs.
Right. Even though expressing R in terms of this is not quite obvious, because you see, R is related to a choice. And so how does that choice manifest itself? So it turns out that you have to actually, to get a connection, you can use these local connections on every UI, which is the zero connection, and then glue them together using some partition of unity. So you need to throw in some extra data of a partition of unity. And then the answers that you will get will depend on the partition of unity. And they're complicated formulae, so it can be done with some extra data.
So when you say GIJs, are you including the covering of X as part of your data?
Yes, so this is, so in this case...
Makes a covering and you have this
exactly.
GIJs and now you want to express it.
Exactly,
and you probably will have some rules as you change things.
Right, yeah, so you want to know that this is independent of the cover that you choose in the appropriate sense. So. Okay, so what is the setup? So I'm going to discuss, the way I'm going to formulate this is that I'm going to first define, by the way, there are four flavors of these. One is the smooth flavor. One is holomorphic flavor. And then there is Hodge, and then the Rham. And it turns out that even though we are more familiar with the smooth things than holomorphic things, or at least I am, it turns out that these two discussions, in both cases, the Rham discussion is much harder than the Hodge discussion. So for the purpose, for the sake of exposition, I would like to tell you about the Hodge discussion. But then the Hodge discussion in the smooth case is kind of boring. So I'm led to concentrate in the holomorphic concentrate on the holomorphic setup such that we have something that is meaningful. All right, so I'm going to talk about the Hodge discussion in the holomorphic setting, and then as I go along, I say how it should be modified to fit the Rham discussion. Okay, so what I would like to do...
So you're assuming X is a holomorphic manifold now?
From now on, yes. So I want to define two functors. So by C-man, I'm going to just denote the category of complex manifold with holomorphic maps between them. And I'm going to take the opposite category of this and then construct two functors to simplicial sets. So one of them is called HVB for holomorphic vector bundles, and the other one I'm going to denote by omega, which is supposed to tell you this second thing has to do with forms somehow. It's built out of forms. Okay. Now, what are simplicial sets? So probably you all know what simplicial sets are, but let me just say if you haven't seen them and you want to think about them, there are many ways to represent what a space is. For example, you can say these are the points of the space and this is the topology on it by defining what open sets are, etc. So that's one way to present a space. Another way is to say, oh, these are the points of the space and these are its continuous paths. These are its paths of continuous paths, and so on and so forth. And it turns out that this data is, for homotopy theoretic purposes, this is sufficient. It's equivalent to presenting your space as points with topology. So I'm going to talk about spaces, but in the language of simplicial sets, in the sense that the result of each one of these functors is that it eats a complex manifold and it spits out a space, but I'm not going to tell you what that space is in terms of its points and topology. I'm going to tell you what its points are, what its continuous paths are, what its triangles are, etc. So that's what this simplicial set is supposed to denote. And as a result, a simplicial set, let's say if X is a simplicial set, these would be its points, these would be, let's say, its paths, this would be its triangles, and every path has two endpoints. So I have to tell you, if you give me like a path here, which one of these points here is the beginning point and which one is the end point. And if these are the space of triangles, I have to tell you which one of these paths here is like this side of this triangle. That first arrow denotes that. Which one of these paths here is the second side of this triangle, and so on and so forth. So these arrows, you have this sequence of sets with maps between them, and that's supposed to be one presentation of a space. Okay, so and then what I would like to do, the fancy kind of language for saying what this is that I'm going to define a simplicial presheaves on complex manifolds, but I'll try to avoid that language. The idea is that in a functorial way, you assign a space to a complex manifold. And so I have two ways of doing this, and there should be some natural transformation between them, which I'm going to call the Chern character. Okay, so let's see. Let's maybe start with HVB. So far, so good? So what is HVB? So HVB is supposed to take as an input a complex manifold. So let me call that U. U is a complex manifold, some arbitrary complex manifold. And then it's going to give you some space. And I'm going to tell you what that space is in terms of what its points are, what its continuous paths are, etc. So what are the points of this space? So the points is going to be the set, and I'm going to put in quotation mark sets because it's not really not going to be a set. It's only a set in the sense that set of all sets is a set. It's going to be a class, but there are tools to deal with this type of craziness. So this is the set of all holomorphic vector bundles with a holomorphic connection.
Over U.
Yeah, this is all bundles over U with a holomorphic connection. Or if you would like, I can say this is like all ways of decorating. You have the standard zero simplex, and it's all the ways of decorating this zero simplex with labels that are given by holomorphic vector bundles over U with holomorphic connection. Now notice that holomorphic connections are very rare in the sense that if a vector bundle, if a holomorphic vector bundle admits a holomorphic connection, is fairly trivial. Like all the invariants that I talked about, they are all 0. So unlike the case, it's smooth case where vector bundles have connections and they have plenty of them, holomorphic vector bundles rarely have holomorphic connections. So, but nonetheless, there are always vector bundles which will admit a holomorphic connection. For example, the product bundle. Okay. Now, what are the continuous paths in this set? So these would be all the labelings of the standard 0 simplex with things. So what are those? Well, it would be you label the vertices just as you had done before. Namely, you put a vector bundle, holomorphic vector bundle here, and a holomorphic connection on top of this. And a holomorphic vector bundle and a holomorphic connection on top of this other point. And you decorate the edge with a holomorphic map of vector bundles. But interestingly enough, you want that holomorphic map not to respect, or not necessarily respect, the connection. So it's just a map of vector bundles completely ignoring what the connections on the domain and the range were. Right now, this sounds like a kind of not the same thing to do, but it turns out that this is actually exactly the way you want to do it, and you want to exploit the extent to which this feed does not preserve the connections. Okay, so this should give you what the idea of the next thing would be. So this would be all decorations of the standard 2 simplex. So the vertices are again labeled with holomorphic vector bundles and connections. And edges are, let's say, with phi 0, 1, phi 1, 2, phi 0, 2, such that this diagram commutes. Namely, phi 0, 2 is phi 0, 1 composed with phi 1, 2. Strictly. This whole discussion would have an analog where instead of vector bundles, you consider the chain complexes of vector bundles, and then these phis would be quasi-isomorphisms, and then you would say that these diagrams do not commute strictly, but then there is a homotopy between the composition of these two and that. And in fact, this is how we got into all of this discussion, through studying the work of Toledo and Tong, which did something really amazing in the 70s with these objects that are not vector bundles, but kind of flabby vector bundles, chain complexes of vector bundles. But at the moment, this discussion is already rich enough where I can assume these are strictly commuting diagrams.
So this HVB of U is the nerve of the category.
Exactly. So if you are familiar with category theory, you can immediately see that this is what I'm taking is the nerve of the category of holomorphic vector bundles with connection are the objects, and morphisms are isomorphisms of vector bundles that do not respect the connection. Okay, so, and so on and so forth. So, and in the case that I described would be some sort of DG nerve.
Oh, wait, so you said only isomorphisms?
Right now, only isomorphisms. I'm sorry, so where did that holomorphic, so these would be isos, yeah.
Oh, okay.
So these would be isos.
So it's the nerve of the group of them.
Yes, exactly. So this would be a fairly simple space. It's like a one type. But But it gets interesting when you do the chain complex version of this. Okay. So is it clear what HVB is? And this assignment is actually a presheaf or a functor in the sense that if I assign these to U, but what if I have some other V and a map between U and V? So you see that all of this discussion pulls back. And so you're going to get a map between the space, a continuous map, so to speak, from the space that you assign to V to the space that you assign to U. And that explains why I put opposite here, because if a map went from U to V, this goes from the thing that is assigned to V to the thing that is assigned to.
I did not quite follow when you mentioned you can do this with chain complexes.
Yeah.
In that case, you replace vector bundles with connections by what?
Chain complex of vector bundles with connections at each level.
Chain complex of vector bundles is the
Holomorphic vector.
bundle of
Chain
complexes?
Yeah.
Oh, okay. Well, okay.
Okay. All right. So this is what the HVB is. Any other questions?
This isn't really a question, but once you had said what the vertices were, what I was expecting for the higher simplices was some sort of bundle on U cross the simplex that restricted to each point in the simplex was holomorphic and something like that. Is there a way to rephrase this?
There is a way in the smooth sense, in the smooth category. In the holomorphic category, you have to make sense of what the simplex is in the holomorphic category. But let's say in the smooth case, yeah, the way you're supposed to think about this interval actually is that it's like, you see, if you have a map between two vector bundles and connections, especially if the map doesn't preserve the connections, you can think of this as a connection on X cross the interval. Or U, in this case, U cross the interval. Why is that? Because you can pull back the connection. Of course, because the map did not preserve the connection, now you have two connections on the domain. And then there's always a straight path between them. That's going to give you a one-parameter family of connection, and then you can interpret that one-parameter family of connection as a connection on U cross I. But I think that's the picture that you're... So, yeah. Okay, that was a great question. Okay, any other? Okay. All right, so now I want to discuss what this other omega is. So what is omega of U? So I'm going to tell you first what the fancy definition is, and then I'm going to tell you what it really means. Okay. So what's the fancy definition? So from here on, there are two versions of omega. One is the Hodge version, which I'm going to concentrate on, and then the Rham version. And you'll see what the difference is. So what is the, so in both cases is the following. You look at the forms. You look at the forms. These are holomorphic forms on U. And now you adjoin a variable U, little u, where little u is of degree -2. So this is the positively graded complex. In the Hodge discussion, I choose the zero differential on it. And in the Rham discussion, I choose the differential del on it. So this will have a differential d. And d in the Hodge, d is 0. And in the Rham, d is the del. Okay. So I'm going to take this complex and throw in an extra variable u. Namely, I'm going to consider polynomials with coefficients and forms. And now that's a complex that is in positive degrees and negative degrees. So I'm going to quotient it by everything that is in the positive degrees. So now I'm going to get a complex where it's only concentrated in non-positive degrees and the differential goes up. That I'm going to denote by this. This is the quotient complex. And now every time you have a complex like this, there's a way of constructing a space out of it by telling what the points are, what the continuous paths are, etc. This is called the Dold-Kahn construction. So then you apply Dold-Kahn. Now this is not going to give you, this is going to give you something that is slightly better than a space. It's what's called the Simplicial-Abelian group. So I'm just going to forget that it was a Simplicial-Abelian group. Just think of it as a space.
So you don't take into account the multiplication of polynomials?
No, this is just, it doesn't, no. Yeah, the algebra structure, it does not enter. Yeah. And now let me tell you what this Dold-Kahn construction is. In fact, let me tell you if this was kind of, let me just tell you what omega u is by telling you all its points, all its continuous paths, etc. So what is this? So this would be, again, labelings of the zero simplex by certain things. What are those? So it's going to be some alpha 0. This is a 0 form, holomorphic form of degree 0. And then you have alpha 2 times u. That's going to be a holomorphic form of degree 2. That is offset by u so that the total degree is degree 0. And then alpha 4 u squared, ad infinitum. Of course, at some point you reach the dimension of the manifold, and these are 0. Okay, so now what is omega? Now this discussion would be the same for the Hodge and the de Rham. Now, starting this point, the two discussions differ a little bit. So what is omega u of 1? What are the continuous paths in this space? Well, the continuous paths in this space would be labelings of this one simplex. So over here, of course, you have the alphas. And over here, you have something else, beta 0, beta 1. And now over here, I'm going to put something, let's say, some edge, which is E. So you have E1, that's a 1 form. But then I multiply it by u. That becomes something of degree -1. And then E3 u squared, plus etc. Now this difference between, in both discussions, what you want is that the d of this guy becomes the difference of these two. But in the Hodge discussion, d is 0. So that just means the sum of these two must be 0. In the de Rham discussion, it says the sum of these two is not 0, but it's killed by that.
So I got a question. When you say Hodge and de Rham, you're fixing the whole, your underlying U is holomorphic.
By U is a complex manifold, yeah.
Always. And
well, it exists here, so it's a complex manifold.
So you look at the Hodge and de Rham theory of...
Yeah, there are two versions of this.
Manifolds. So you're not saying anything about smooth today?
Not today, yeah.
In the Hodge case, this omega u is a product divided by the plane spaces, right? It's homotopic.
Yeah, exactly, yeah. Precisely, yeah. Yeah. Okay, any other questions? This is a good time to take a break and ask questions. So let me just say what the triangles are. So what is omega u2? Well, of course, these would be labelings of the standard 2 simplex. These are alphas, beta, and the and then you have E1 u plus E3 u squared. These would be elements of total degree -1. And then similarly, things here. I don't know if I want to write them. These are like the F's, F0. Maybe these are the G's, G0. And then there's something, let's call it H. This is H0U. So it starts with degree -2 plus H1U squared. I'm sorry, H2U squared, degree -2, etc. And again, in the Hodge discussion, you see, previously in the Hodge discussion, there was no constraint on this. This could be anything. It was only that the difference of these two must have been 0. Here, now there is some constraint on the things that are put here, because this sum, alternate sum of these three things must be 0 in the Hodge discussion. In the de Rham discussion, they could be non-zero, but they should be killed by that, in the sense that del of this guy must be the difference of those things. Those three things. Okay. Okay, so now we want to construct CH. So CH is supposed to be a continuous map, so to speak, from it's a natural transformation. So that means for every U, it's going to be a continuous map from HBB of U to HBB to omega of U. Remember, HBB of U is a space. It has points, continuous paths, continuous maps of triangles or paths of paths, and the same thing here. And if I want this to be a continuous map, that means I have to say how points go to each other and how a continuous path is sent to a continuous path, etc. So in effect, I have to tell you what I get when I put 0 here, and next time what I would get if I put 1 there, etc. Okay, so what do I get when I put 0 there? So what would this be? So what's an element here? Yeah, it's a declaration of the 0 simplex with a vector bundle and a holomorphic connection. And yeah, it's a vector bundle with a holomorphic connection on U. So it's a vector bundle over U. Well, as I said, holomorphic vector bundles that admit a connection hardly have any invariant. So the only thing I can think of is that I assign the rank of rank of E. So in what sense that's something over there? Well, rank of E is the simplest 0 form you can imagine. So I just put alpha 0 to be the rank, and then the rest are zeros. 0U. So in some sense, it's as an invariant of holomorphic vector bundles with connection is really nothing. It's very boring. Okay. Okay, so now what is CH of U1? Well, that's going to give you, go from HBB of U1 to HBB of, I'm sorry, to omega of U1. Okay, so what could this be? Well, it's an element here is a declaration of the 1 simplex with 2 vector bundles with holomorphic vector bundles and holomorphic connections, to which I've already assigned a kind of very trivial thing. And now I have a isomorphism, and this isomorphism does not preserve the connections. So I'm going to explore that. I'm going to say, well, I'm going to assign to this what I would like to give here. Well, well, I would like to give a decoration of the standard one simplex again, but now with forms. So of course here I have given rank of E0 plus 0 U plus etc. Here I have given rank of E1 plus 0 U etc. And here I have to put something. Well, here now the difference between the de Rham discussion and the Hodge discussion appears in this case. So I'm going to first tell you what I put in the Hodge discussion. So the Hodge discussion is going to be very simple. What I'm going to put, what do I want? I want E1 U plus E3 U squared, etc. So I have to tell what this one form is. So I'm going to write the trace of G inverse, no, sorry, phi inverse. This is phi01, right? Phi01 inverse D of phi01. Now what do I mean by D of phi01? The D of phi01, D of phi basically is going to be, you see, you have two connections, so I can apply the connection and then apply phi, or I can do it the other way, apply the phi and then apply the connection. Of course, these are different connections. This is like connection 1 and connection 0 and connection 1. And if phi preserved the connections, of course, this would have been 0. So the fact that it didn't preserve the connection tells me this is something non-zero, but this is going to be something whose values are, there's a one form, but whose values would be homomorphisms from bundle E0 to bundle E1, and I have to bring it back to be a self-map so that I can take trace, and that's why I compose it by that.
So why is that a one form? Sorry?
Because I'm differentiating, see, like for example, what is, I'm sorry, this, nabla 0 phi nabla 1. So what's a connection? A connection, one way to think of a connection is that it goes from sections of E to one forms on the base tensor sections of E. So you see, like phi is a map, so it eats a section, gives you another section, and now this takes nabla of it, so it gives a one form. Okay, so that's going to be a one form. And now, this is in the Hodge discussion. And in the de Rham discussion, I have to actually put, this is the only thing I put in the Hodge discussion. In the de Rham discussion, I have to put infinitely many terms. And that's why the de Rham discussion becomes more complicated. So for example, on this one, I'm going to put the trace of the same thing in the de Rham discussion to the third power. And then next thing to the fifth power, etc. This would be in the de Rham. Okay. Now these things are kind of familiar because this is the left invariant. That form phi inverse d phi is a very familiar thing to people who work in differential geometry. It's just the Moret-Cartan form, left invariant form on a Lie group. And even the higher terms that I put are familiar. Those are called they call the odd Chern character. Okay, but now in the next starting what you assign for triangles, you start seeing new things that I hadn't seen before. For example, what is CH of U2, which goes from holomorphic vector bundles U2 to omega U2. So here you have 0, 1, 2. So you have E0, nabla 0, E1, nabla 1, E2, nabla 2, phi 0, 1, phi 0, phi 1, 2, phi 0, 2, and then here, nothing. These will commute. And what I'm assigning to this, I have to assign a declaration of the here. So in both discussions, I had assigned rank of E0. By the way, did you check that it actually lands where I had said it lands? Because the difference between the ranks must be, in the Hodge discussion, 0. But that's what two isomorphic vector bundles have. The ranks are equal. And in the Rham discussion, it says that these infinitely many things that I had put, their D must be 0, but that's also known, these are closed forms. They're called Hodge Chern characters. So far everything matches. And so you have rank of E1, rank of E2. Then here I had put, let me do the Hodge discussion because it's already interesting. So I dropped the indices, so it would be trace of phi, d phi, trace of phi, d phi, trace of phi, d phi, phi inverse d phi, sorry. And now, what I want to put here, it would be expressions like this. You take the d of phi 0, 1, d of phi 1, 2, and then phi 0, 2 inverse trace. Now this is something I had not seen before, because if you think of what this is that, you know, this is the composition of, this is like phi 1, 2 inverse phi 0, 1 inverse because of that condition. And another way to write this, because trace is cyclic, is that you take the trace of, it's like you have phi 0, 1 inverse d phi 0, 1 times d phi 1, 2 phi 1, 2 inverse. That's interesting because it's the product of the left invariant form with the right invariant form, which is quite interesting. And this is already, in the Hodge discussion, this is the only thing that you put, but in the Rham discussion, you have to put infinitely many interesting formulae, that is, combination of left and right invariant forms. So basically, in this case, would be all powers of the left invariant and right invariant forms mixed in all possible ways. And yeah. And then the coefficients are actually quite interesting. They're expressible in terms of gamma functions and beta functions, and some interesting integrals. Okay, so the idea is that this is and the way I've discussed it, I've set it up, it should be fairly easy to check that not only this is for every U, this is a map of simplicial sets. It's very pictorial. You just restrict the faces to get these discussions. And then it should be also easy to see that when you pull back, the values correspond. So. Okay, now you may say, okay, you did all of this, but what is this good for? Okay, so let me say what some of the things you can do with this. So before telling you what these things are good for, let me just say a few words about inverse limits. What's the inverse limit? So see, inverse limits, they are like if you have a bunch of sets or spaces and maps between them. Let's say you have one single map, single map, single map. What's a point in the inverse limit? Well, points in the inverse limit is a point in here and a choice of a point in there, but it can't be just any point. It should be a point so that this map sends it to that point. And then would be a choice of a point in the preimage. And a point in the preimage of that. So an infinite sequence of points that are related by these maps would be a point in the inverse limit. So, but now, let's make our diagram a little bit more interesting. You see how I defined what a simplicial set was? A simplicial set or a space was a collection of things where So I want to get a diagram like this where things where I want to take inverse limit. So how do I come up with such a thing? So example. So suppose X is given. This is like some complex manifold. And now I choose a cover of X. Imagine that's a good cover. It's a cover that has all the ideal properties you want. Okay, so now let's say this cover U is collection of some UIs. So you see, X is not the thing that I'm going to put inside that Chern character business or HVB or omega, but rather X is covered by U's, and these are the U's that I'm going to put in there. Of course, since I may have a million of these U's, I would get millions of spaces. For every U, I get a space. But not only I want to just apply it to U's, I want to apply it to what's called the Cech nerve of U. But what is the Cech nerve of U? Cech nerve of U is itself is like something that again has things in of dimension 0 of something of dimension 1. The technical definition is that these are this is a simplicial manifold instead of a simplicial set. But you can think of it as something like a simplicial set, except that the individual things that was like the set of 0 simplices, now it's the manifold of 0 simplices. This is the complex manifold of continuous paths, etc. Okay, so what are these? So this would be the disjoint union of the UIs. This would be the disjoint union of UIs intersection UJ. Disjoint union of UI intersection UJ intersection UK, and so on and so forth. And immediately you see that there are two maps this way. Because if you have, let's say, UI intersection UJ, you can once embed it in UI, and another time you can embed it in UJ. So you get two maps, and then three maps this way. So this is what a simplicial manifold is. It's an example of a simplicial manifold. And now I can take my HVB, for example, and apply it to this simplicial manifold. That means I apply it to this. That's going to give me a space. It's going to give me a space. What is that space? It's built out of whose points are vector bundles and connections on each UI, whose paths are, etc. And then I can apply it to this also. That's going to give me another space. And apply it to this also, and I'm going to get another space. So I get infinitely many spaces, but now remember, because this HVB was a contravariant thing, now these arrows would switch. So technically, this becomes a cosimplicial space. Okay. Now, if you have a cosimplicial space, one nice thing to do is to take inverse limit. So you want to kind of glue them all together. Okay, so you have, how do I take inverse limit? Well, it depends on whether you're a set theorist or a topologist. Because if you're a set theorist, you say, well, inverse limit is the thing whose a point in the inverse limit is a point here and a point here where both of these maps are send this point to that point. And then a point here where all three of these maps are sending this point to that point. It's fairly restrictive. You may never, and this goes ad infinitum. So you may never ever find a point there that satisfies all these requirements. So the topology says, I don't care about the exact identities. I only want that when I look at this, this point, well, this sends it somewhere and this sends it somewhere. I don't care if they are identical, but as long as they are like connected by a path. And I take that path as part of the data. So a point would be a choice of a point here and a path there, such that the image of this point under these two maps would be the endpoints. And again, a choice, I don't choose a point here, but rather I choose a triangle. But I want that triangle to be so that the image of this path under this map is the first edge. This will send it to the second edge. So a point inside the homotopy inverse limit, so to speak, would be a point in the first space, a path in the second space, a triangle in the third space, and so on and so forth. And now if you want to know what's a path inside this, would be a path here and a square here. Well, of course, the square is broken into maybe two triangles, and a prism there, where this prism is built out of three tetrahedra, and so on and so on. So there's a nice combinatorics. This process is called homotopy limit, and sometimes also called the totalization. This is a totalization of a simplicial space. Co-simplicial space. Yeah. Okay, so what I've done, let's review what it is. I'm going to review what I've done in this talk so far. I have HVB. I have HVB. That's an assignment to every complex manifold that assigns a space. And I have omega. That's also an assignment. Technical term is that these are simplicial presheaves. And then some map between those assignments. That's like a natural transformation. That's called Cech. So what I want to do now, I took some X and covered it with open sets. These are the U1, U2, etc. And then I did the check nerve. That was a simplicial manifold. Then I applied HVB to that. Now that's going to give me a co-simplicial space. And then I also apply omega to that. That gives me another co-simplicial space. But now I want to put them all together using some inverse limit, but topologists inverse limit. So I take tot of that. And I take tot of that. Now this would be a space, and that would be a space, and this is a continuous map between them. So I've constructed a continuous map. Okay, now you want to understand what this...
CH induces a continuous map between
Right,
topologies.
exactly. So, okay, what does this continuous map do? Well, let me tell you what it does on points. It has to send a point to a point. So let me say what it is in degree 0. Okay, what are the... You have to study what this thing is. Well, what this is, it turns out that it is, you have X. X has a cover. And on it, a point is a holomorphic vector bundle. This holomorphic vector bundle itself may not admit a holomorphic connection, because if it did, it would be fairly trivial. But I've already chosen a connection on each UI. So there's like a holomorphic connection here, holomorphic connection there, holomorphic connection there, and these are kind of incompatible. Because if they were compatible, that would say the bundle would have been fairly trivial anyway. And then what I've assigned to this, I've assigned some element in tot 0 of this. Well, what is that? When you look at that real closely, you see that this actually gives you the Cech. You can take the Cech complex of forms. Well, of course, in the de Rham case, it would be with the del, and then the Hodge case would be without the del. And now that's going to be a chain complex, and I can assign, make polynomials out of this and truncate it. That gives me a, and then I take elements of total degree 0 that are closed. And so what that's going to be my Chern character assigned to.
So that's a point in that totalization?
That's a point. This is the set of all points in that totalization. So so I made thank you. So it sends this to the CH of that thing. Let's say E. Thank you. E over X. So it would be CH of E. In there. So this would be that, and this would be the set of all such things. Okay, so this is and you can write down the formulae explicitly. You can just say what, like if I give you in terms of transition functions, you can just swallow this and write the explicit formula in the Cech complex. It's a little easier to do it in the Hodge case than in the de Rham case, but you can do both. But now the nice thing about this is that now you actually got not invariance for bundles, but you also got invariance for bundle maps. And you also get invariance for sequences of bundle maps.
So you get like higher classes.
And you get higher classes, and those higher classes would become even more interesting when you take the chain complex of vector bundles, because then the diagram, you have like, this is not just a sequence of bundle maps, it's like a homotopy. So it gets fairly interesting.
How much do all of these higher classes know about what you started with?
Well, it's the objects here is like it knows about this category. The objects are vector bundles, and of those you're recording the characteristic classes. And of the maps, you're recording characteristic classes of maps and higher. Characteristic classes of homotopies. So these are.
There's no reason to expect that this is close to an equivalence, right?
No, it won't be an equivalence, but I don't know how to answer that question. You need a metric to kind of measure, like, to what extent it is close. There's some invariant. Okay, but yes, please.
Something that you can do in the side is that you can get the Atiyah class.
Yes.
Of the manifold.
Yeah.
Can you recover the Atiyah class from?
So in fact, this is in the Hodge discussion. Atiyah wrote down formulae for the invariance of the vector bundle in terms of Atiyah class in here. These coincide with that. But the de Rham discussion is new. And the story about the invariance of the maps is new. Atiyah only did it basically on, the classical discussions all are at the level of points, whereas the space has points, paths, triangles, etc. Okay, but now you may say, okay, well, what else can you do? This is like too much work for just one application. So, well, the interesting thing is that now you can do a lot of things, because, like for example, you can take a space, let's say you take some x, and let's say this x has a g action. Let's say x is still a holomorphic vector bundle and has a g action. And now you can like you can immediately do, instead of doing the check nerve that we did for cover, you can say, okay, I don't want to take a cover at all. In fact, you can take a cover as well, but let me just simplify and say you don't take a cover. But you can form like X cross G, X cross G, cross G. This is called the homotopy quotient construction of this action. And it's just as good as those disjoint union of UIs, disjoint union of UIJs, this UI intersection UJ, etc. Because these have the same format. So again, I can apply HVB to this discussion, then I get a cosimplicial space, then I can apply omega to this discussion, and I get a cosimplicial space. Totalize it. CH map would give you a continuous map. You can say, what is it on the vertices? Well, on the vertices, it turns out that it gives you some versions of equivariant Chern character, again in the Rham case and then the Hodge case. And you can combine this idea with idea of having a cover. We can make it a bit more interesting. And more generally, you can, if you like fancy language, you can apply this to any stack, for example. This would be like the quotient stack. So you get some invariance always. This is what's good about this. It gives you the flexibility of doing all these constructions fairly functorially, and not only you get invariance at the level of points, but you get relative invariance. I think maybe this is a good place to stop.
Questions? In this example of the homotopy quotient,
Yeah.
what exactly are the points of the totalization? They're
So,
G equivariant,
exactly.
holomorphic vector bundles on X with some arbitrary connection.
With some arbitrary connection, and it measures, the invariant measures to what extent the G action preserves the connection. And then you can also do, if you combine, this is when X is covered with one open set. But you can also choose a cover and then make it G equivariant by adding more opens.
Yeah.
And now you can form a bisimplicial thing. And you can do diagonal of that, and then it gives you all the equivariant Chern characters. And it gives you a Rham version and a Hodge version, and those would be a degree, degree 0, but you get degree 1, degree 2. Yeah.
Thank Mahmoud again.
Okay. Thank you.